Hello and welcome to this Open Automation Software Builder Series episode on how to work with MQTT messages and JSON payloads. In this episode, we're going to work through a hands-on example of how we can source data from a device, process this data, and finally, how to visualize this data. We're going to use a real Modbus RTU device connected via serial port to an LTE router, which acts as a Modbus client and an MQTT gateway. This router will poll the RTU using Modbus and construct the MQTT payload and then publish it to OAS using a topic that matches a tag name in OAS. The OAS broker will receive the message and assign the payload to the tag. Once the payload is ingested, we will use OAS calculation tags to extract various pieces of information out of the payload. This will include the site ID, the digital inputs, an analog input, and the digital outputs. Finally, now that the data is stored in a set of tags, we can visualize these tags in the OAS UIEngine. In the following slides, we're going to explain the concepts one step at a time, and then we will use OAS and UIEngine to create a real implementation. All of the devices used in this episode are real and are connected to actual digital and analog signal generators for testing. This is an example of connecting a legacy device such as a serial Modbus RTU and converting the protocol to MQTT so that we can use a message-based publish and subscribe protocol. It is of course also possible to configure the router as a serial to IP converter and use the OAS engine to poll the Modbus device directly via the router. Similarly, it would also be possible to connect Modbus TCP devices using Ethernet and poll them directly via the OAS engine as well. The benefit of this particular architecture is if the LTE connection is lost, the router will continue to poll the RTU locally and buffer the MQTT messages. Once the connection is re-established, the messages will be sent. So, let's get started. The RTU that I'm using here is an old Broderson RTU8 data logger. It's no longer manufactured, so you could say it's well and truly legacy. I'm going to use it because I have one available in my test rack and it supports Modbus RTU over an RS-232 connection. And this will give us a good example of how to integrate with legacy devices. So let's have a look at the data that is presented by the logger. This image is taken from a Broderson development tool, but what it shows is a memory map of registers. Each number you see is a 16-bit short integer. This means the 16 digital inputs are represented by one 16-bit number. The analog inputs, on the other hand, have a resolution of 12 bits, so the maximum value is 4095. There are also 8 digital outputs. I've highlighted the memory positions that we are interested in. To read the data, we'll use the holding registers function. The Modbus addresses are shown in brackets. So for example, the digital inputs are at address number 3, the analog inputs at 4, 5, 6, and 7, and then you have the site ID at address 14 and the digital outputs at address 17. Whatever your device is will have similar Modbus memory map, so you would have to first understand where your data is before you can access it. Let's now move on to how we will read this data. For this implementation, I'll be using a Teltonika RUT956 LTE modem, but for the purpose of testing, I've connected it via my Wi-Fi network. I've connected this device using an RS-232 serial cable to my RTU. What we need to do next is configure the Modbus serial client in the router. This client sits in the RUT956 and handles the task of regularly polling the RTU. In this case, I've set it to a 1-second interval. The client is configured to use the read holding register function with a 16-bit data type, and it will read 17 registers starting at address 3. Now we need to construct the MQTT payload. Using the data to server function on the Teltonika, we can create a new collection, which is basically another word for a message. In this case, I've chosen to create the JSON template with an RTU8 data attribute. The data then sits inside that attribute. The timestamp is represented by the T attribute, and the value is using the V attribute. The percentage variables are substitution variables where the Teltonika will insert the data. The way this works is the Modbus serial client in the previous slide will be automatically picked up by this MQTT configuration. Normally, if you have multiple Modbus polling requests to the same RTU, you can filter the collection in the MQTT settings to only send specific client requests. You can see the final payload here, and you can see all of the values have been added as an array. We can now configure this to be sent to the OAS broker. In the data to server configuration, I've set the MQTT details to point to the OAS host on port 1883, which is the standard MQTT port. And set a client ID called device123. The MQTT QoS or quality of service is set to 0, but you could use whatever value is more appropriate for you. So now let's look at the detail of the topic field. Let's go through how the OAS MQTT broker works. The most fundamental representation of data in the OAS system is the tag. This is a single unit of data and is made up of a value, a timestamp, and a quality. Any data that you want to store in OAS has to be contained in tags, so we need a way to get the MQTT payload into a tag. The way OAS deals with this is to match the MQTT topic with a tag path. So let's first create a tag. I'm going to create a tag group called MQTT, and then I'll create a tag called device123. The value parameter is where your actual data is stored. So this means the topic name will have to be mqtt.device123.value. In addition to this, we can set the tag to a JSON data type for some extra validation. At this point, we should now be receiving the payload you can see here into this tag. What we need from this point is to extract the information that we want out of the payload. For the purposes of this video, we want to extract a few key parts of the payload. In this table, you can see the registers that we are interested in. We're going to extract the site ID, a digital input, an analog input, and a digital output. Remember that we will need to create a new tag for every unit of information we want to extract. The tricky part is that the payload stores all of the values in an array, and the digital inputs and outputs are encoded as integers. So we'll need to do some bitwise operations. For these kinds of tasks, we will need to use OAS calculation data source so that we can use some JSON functions as well as some binary functions for dealing with bitwise operations. We'll go over that shortly. Let's start with the site ID. When dealing with JSON, we will primarily use the JSON query function, which allows you to use JPath syntax to query the data structure. You should be able to find plenty of resources online on how to use this syntax. The first argument of the JSON query function is the tag value. In our case, this is the tag where the MQTT payload is written by the OAS broker. mqtt.device123.value. Remember that the tag has to use the fully qualified tag path and includes the group name followed by the tag name followed by value. In OAS calculation formula, tag names must be surrounded by square brackets. The second argument of the JSON query function is the JPath query string. The first part of this string is the $, which represents the root of the data structure. We'll now work our way down to where the site ID is stored. The next element is an object property, so in this case it is RTU8_data. The next property after that is the V property, where the value is stored. So far we've simply referenced the name of the object property. Now we have an array, so we need to use array indexing. The site ID value is at index 11 in the array, so we'll set that here in the array indexer. Now the query is complete and we have our site ID. In our overall diagram, we can now add the site ID. I've created tag group called device123, where I'll group all of the tags related to device123 together. In there, I've created a site ID tag and used the calculation data source with the calculation formula that we just discussed. We can set this one to an unsigned short integer, as the RTU8 data types will never exceed a 16-bit integer. Now let's move on to some inputs and outputs. For the digital inputs, we're going to read digital input number 1, which based on the payload data is 39 and has a state of true. Before we get onto writing the next calculation formula, I'll just briefly outline the bitwise operation. Since the number 39 can be represented as 16 bits, we can AND each of these 16 bits with a bit mask that results in setting every bit to 0, except the bit position that we are interested in. In our case, we start with the binary number 1, and then we shift it by the position number of the bit we want to check if it's true or not. In our case, we don't shift it at all because we want to test the first position starting from right to left. The comparison to 0 at the end is simply conversion to a boolean so that we get a boolean response. Let's now see how we can do this using a calculation tag in OAS. As before, we need to use a JSON query function to pull out the digital input value from the payload array. In this case, we want index 0. Now that we have digital input state, which is the number 39, or the binary representation shown above, we can do the bitwise operations. In OAS, the bitwise operations are also functions, so like we would do in Excel, for example, the query now looks like this. The bit shift left, part in green, handles the shifting, and the surrounding bitwise AND function takes care of the AND operation between the binary number and the mask created by the bit shift left function. The end result is then checked to see if it does not equal 0. We can now create a tag using this calculation. Here you can see a digital input 1 tag created with a boolean data type. We can repeat this same process for other digital inputs, but you just have to remember to change the bit position in the bit shift left function to whatever bit position you want to check. For digital input 1 it was 0, for digital input 2 it would be 1, and so on. Let's now move on to an analog input. Reading the analog input is very similar to the site ID. We'll again use the JSON query function to extract index 1 from the payload array. But there's one more thing we need to do, because the number 2052 shown here is a raw number and is not the actual voltage being measured at the input. To solve this, we need to apply some scaling. The input range of an RTU8 analog input is 0 to 10 volts, and the raw value for this range is 0 to 4095, because the analog inputs are encoded as 12-bit numbers. There are a few approaches you can take. The first is to hardcode the scaling factors into the calculation formula directly, as shown here. The second approach is very similar, but you could create 2 more tags to hold the scaling and range values, and then reference those in the formula, so they're not hard-coded. And the third method is to use the gain and offset feature of an OAS tag. But to use a gain, you'll have to put in the ratio, which is 1 divided by 4095 times 10. So now we have an analog input, and we can create a tag for that with an unsigned short integer data type. Again, we could repeat this for the other 3 analog inputs. So now let's do one of the digital outputs. These steps are very similar to the digital inputs. The only difference is that there are 16 digital inputs but only 8 digital outputs. Nevertheless, the process is the same. We need to extract the value out of the payload array. In this case, the outputs are on index number 14. And we are going to look at bit position 6. So now we can do the bitwise operations to test bit number 6, which is the 7th bit. And just remember that the bit starts at position 0. And finally, we can create a Boolean tag for this digital output number 7. Alright, so we've got a few tags here with all of the values extracted. The neat thing is we didn't have to write any code to do this, and we can use the OAS calculation functions to extract these values. I'm going to use the OAS configure application to add my tag groups, my tags, and then set up the calculation functions. So first of all, I'm going to add a group called MQTT. And then I'm going to add a tag called device123. This is the tag where the Teltonika will publish the messages. So we're going to set that to a JSON type and apply that. So as you can see, the data is already coming in at a 1-second interval. Here is the payload, which you can view in this little JSON viewer. You can see here is the digital inputs, analog input 1, 2, 3, 4. Down here is the site ID and the digital outputs. T is the timestamp and the RTU data object name to contain the entire payload. So we can now add those calculation tags. So I'm going to create another tag group called device123. So this is going to hold all the tags for device123. So the first thing is let's do the site ID. So I'm going to add a tag called site ID. And then we will make that an unsigned short. And the value will be a calculation, the data source. And we'll edit this calculation and put in the query that we discussed previously. So we're getting the MQTT device123 value tag, extracting the RTU data.v at index 11. So apply that. And here we go. So that tag now holds our site ID. Now let's add another tag, and we'll call this one digital input 1. This one's going to be a Boolean type because it's a digital input. Again, we use calculation. We're going to put in here the function for reading the digital inputs, which were at index array 0. We want the first bit position, which is bit shift left 0, and it does not equal 0. Apply that. So currently that state is true. Now I've got an application here for interfacing with the simulation. So what I can do here is toggle this first input and write that. And you can see here the input changed to false. I'll toggle it back to true, and we're back to true. You've also noticed here, whilst the data continues to come in every second because the timestamp's changing, the calculation determined that the value or the state of this digital input isn't changing. So this timestamp isn't changing here because it will only change the timestamp if the value changes. So effectively this timestamp was the last change value timestamp. Next thing we can do is add another tag, and we'll call this analog input 1. This one's going to be a unsigned short, another calculation tag, and we're going to make this one the JSON query with the scaling factor of 4095 divided by 4095 times 10. So that should give you about 5 volts. Now again, we can do some testing here. I've set up an analog input simulation tag previously, which allows me to write an analog output to my simulation device. So currently I've set it to 500, which is 50%. I can change this to something else, like for example 25%, which should be 2.5 volts. So let's go check, and there you go. So the value is 2. I'm actually going to change this to a double float, because then we can see some decimal places, or a single float. There we go. So now we're getting more accurate analog input readings. Now we're going to add the digital output. So we're going to put digital output number 7. And that's going to be the 6th bit position. So we'll change this to Boolean, change it to a calculation tag, and then we'll put in the JSON query and bitwise operations for device123.value, array position 14, which is the digital outputs, and the 6th bit position, which is digital output number 7. Apply that, and there we go. Digital output is currently true. So now that we've added all our tags, we can move on to some visualizations. Okay, let's go have a look at UIEngine. I'm going to log in using my OAS credentials. I'm going to add a project here, but let's call this dashboards. Okay, and then under the dashboards projects collection, you could say, I'm going to add a new screen called device123. That's good. So I'm going to edit this, and I'm going to go to settings. Now the cool thing is, as you create a dashboard for different devices, instead of having to constantly put in the tag prefix on the names, I'm going to put in here device123 dot, which will be the tag prefix to every tag that we add. We're also going to make this the home page, and let's make this a fixed size of 1028 by 1024, sorry, by 720. It doesn't really matter, you can do however you want. Just for fun, let's make this a black background. Okay. Now we can run this already. It's currently a blank screen. Alright, let's start by adding the site ID. We'll change the foreground color to white, and we're going to make this text site ID, and let's make it line up in the middle. Actually, let's make it line up on the right so that it can sit there, and we're going to use the grid to line it up on these two squares. Now let's add another label, and we're going to take the value of the site ID and we're going to pop it in here. Okay, we're going to use foreground of white again, and we're going to line it up. And now, so the text, instead of being a static text, we're going to make the default dash, but we're going to assign a tag here. And remember that we've set the tag prefix to device123 already, so we don't need that bit, we just need site id.value. Okay, and that's it. So we can just test that, and there you go. So the site ID is now coming out. So let's pull that a bit closer. Maybe we can put a little bit of padding on the right hand side. Just a bit of padding there. Okay. Now let's make this font a little bit bigger. Maybe that's okay. Yep. And we can play around with some of the other settings. For example, let's give it a different color background. Maybe a little bit darker. And maybe a border, maybe 2. We're not going to be able to see that because that's black. So let's change the border to white. There we go. 208. All right, now let's get in some digital input states. So we're going to use a label again, and we can make the background color dependent on the state. So let's use a red color for true. So the tag will be device123.digitalinput1.value. There we go. And the default color will be green. Let's just see if that's working. Okay, that's working. So it's red when it's on. And then let's toggle the input here. And then green when it's off. Back on, red. Okay, now we don't want this label in here. So we want to make sure that the text is nothing. In fact, what we're going to do though is we're going to set this to digitalinput1.name, or we can say di01. Okay, now let's line this up in the middle, make it a bit bigger. Whoops, not that big. And maybe set it to a white color and try that again. Nope, that didn't work. So that's because I didn't set, it's because I was using a tag, which is not right. I have to use just a static string. There we go, run. Okay, let's try that again. Change that to 0 and change it back to 1. Now let's add the digital output. So make a copy of this, and then we can rename that to D07. Background color will need to be sourced from digital output 7. And we can try and run that. There we go. So that's now reading the state from digital output 7. And then we can do the analog input. So let's add a gauge. We want this, there's lots of options with the gauge, all depending on how you want to display various parts of it. So we could have some numbers on the middle. You could have some tick marks. So the value is going to be 10 maximum. Okay, and then we want the value itself to be coming from a tag. So site ID device123 analog input1.value. Okay, so let's run that. Okay, so that's the correct value, but it just doesn't look so good. So we want to check if we can configure the numeric format. So that would be something like 0.0 for one decimal place. Can add some V at the back there for volts. We could make, there's a few offsets we can set up as well. The other thing is the gauge name at the bottom. So let's have a look. There's the label gauge down there. So let's call this the AI01. You can also adjust where this goes. Let's put that further down. We could also put the label further down, but then it sort of overlaps a little bit. Let's make it a little bit smaller. We can put some padding on the bottom, maybe just a little bit more. Nice. And then let's change this value because it looks a bit silly. We can't test it that way. So let's set it to 5. There we go. The other thing we can add is some tick counts. So if we set the minimum tick counts at 1, sorry, we want 3 of these, and we want the tick locations to be on the inside. So we're going to have 6 major ones and 3 minor ones. So if I increase that to 10, we have a lot more per tick, right? So we only want 2 for every half, and we want this to have 5 so that it's divisible by 10, and then maybe 1 tick mark for each volt. So, sorry, I need to add 4 because it's the number of ticks in total. Oh, there we go. It actually counts the last tick as well and the first tick. So that looks good. Let's run that. There we go. So now I can also test the analog. So if I go to my analog simulation, set that to write a new value, let's say 650. There we go, 650, 6.5 volts. So to summarize, in this video we had a look at how to connect a Modbus RTU serial device to an MQTT gateway, get this data through to OAS using MQTT messages, and then how to extract the payload using JSON calculation functions and create the tags where we then put the data, and then finally present all that in UIEngine. Hopefully this has been useful to you, and thanks for your time.